Other way, back out here a little bit. Okay, so let's see. I have here two cell phones that are connected. That is, in the sense they have exchanged phone numbers. So why don't one of you call the other one?
That's soon I actually have service on. Yes.
That's pretty big. Maybe the bigger phone should call the smaller phone. I don't know enough oil to go on that bigger phone. Mr. Hetherington, why don't you call Mr. Should be better. Yeah, it takes a minute.
You might want to turn your ringer.
Well, I did turn it off. I already took the call.
What's that?
Oh, we're good to go.
Okay, have you called him?
Yeah.
Okay.
Yeah, it's connected.
Oh, your ringer's off.
Yeah.
Can you turn your ringer on for a minute,
Okay.
please? Yeah, I know. I've never done this. Turn a ringer on in class.
So hang up on Ben and then call.
I guess so. I guess so. Hang up
Oh,
on
God.
that. I just want the sound here, so as part of the demonstration. I'm just taking your word for it. But at least we can hear your phone.
Got it.
Yeah. What kind of ringtone does it?
One of the
Mr.
default
McKay?
ones.
Okay, that's good. What does this say about your personality? All right.
I used to call stuff.
Now we're going to do it again, but wrap your phone up in the aluminum foil.
Okay.
And shouldn't have any gaps.
Oh, well,
Try to get it. Now I know there's some holes now in the foil. It's been in my pocket for about a week.
That's pretty well sealed.
Okay, try it again.
Cohen.
Now we're going to get to hear his voice. Oh!
Oh, man.
It worked! Wow, that's not supposed to happen.
My phone is that good. It is just that good.
Hey,
Wow.
Yeah.
do you think that would cover your phone because your phone's small?
Mine is smaller.
Oh, well then, here you go.
And yours is more like my phone. Yeah, yours looks a lot like my phone, so I don't know what the difference is. Is it on? Okay, I
It is
don't know.
on.
I don't know.
It's definitely on.
Oh, do you have his
Bring it
number?
back.
Oh, yeah, I can call him.
Somebody's got Mr. Fox's number?
Raise to see who called.
Like I get phone calls.
Call it.
Okay, it's calling. Mr. Fox. Good. Have you gotten the voicemail? Usually they send you the voicemail.
Not yet.
Not yet. Still trying to call him.
Does your phone actually have service? Because we are.
I think it does.
Okay, yeah, it's ringing on there, but it's not ringing here.
Daniel, I'm not sure.
Okay, good. Got to the voicemail. Great. All right. It's kind of fun to experiment with this, where you use a mesh, a wire mesh that is not quite as solid as this, because microwaves will go through if the mesh is big enough, because the wavelength is micrometer wavelength. So, okay. All right. So let's see here. Let's go through the test now, and we're going to do it like usual process. We're going to do the. I got to fix this. We're going to do the usual process of taking volunteers, and of course, you can jump in early and then have more control over what question you ask. Need to. Somebody has told me that the camera in the back is not autofocusing very well, so I'm fiddling with that too. Okay, so definitions, formal definitions, magnetic field and vector potential. Who would like to go? Do you want to just say it out loud, or do you want to try writing it?
I would definitely prefer to say it.
Okay, all right.
So magnetic field, the power, category of quality, activated in the plana by an impetus-activated charge, and which can cause an impetus in a receptive body.
And what is the necessary condition for making a receptive body, making a body properly disposed? Does it say?
Oh, that is a good question.
It's activated charge.
Sorry? It has charge and it's moving.
It has impetus, right?
Yes.
In a receptive body, a charged body which has impetus of a certain type, right?
Okay.
Okay, and so to further elaborate on it, remember this characteristic, if they have the same charge, then like impeti attract and opposite impeti repel. And but there is also a force on the, if it's going in this direction, if they're perpendicular, right? There will be a force in that direction. Okay. Ms. Myers, what's a vector potential, please?
A further specification of the magnetic field such that A gives the potential. I can't read my handwriting.
If you can't read your
I'm pretty
handwriting,
sure it says
imagine Mike's
impetus
situation.
or momentum. It uses impetus or momentum. There's a T per unit charge at a given place relative to reference.
Yeah, potential momentum per unit charge. Yeah, good. And is the I'll stop doing that. It keeps wanting to update stuff. What's on the internet if you're not updating, right? Okay, so in fact that's a good point. I could probably turn this off by turning off the wireless. Okay, turn off the Wi-Fi. That should stop that message, I hope. Okay, so let's see now the vector potential. So you gave the definition as it is here, but to expand it a little bit, if somebody were to ask what the vector potential is, this definition doesn't quite start with the most generic thing. So is the vector potential a substance or a property?
It is a property.
It's a property of what substance? The plana, right? So it's a further specification of the character or disposition of the plana. Okay, and it's related to magnetic field. So, okay, good. Thank you very much. So y'all can relax now. Oh, see, this is the thing about this here. Okay. So I don't know quite how to get it out of this mode. Maybe I can use the. Here we go. Okay, I'll use this. All right. So next, what is the cause of a magnetic field, Mr. Miller?
Impetus activated charged body.
Right. A charged body with impetus. That's right. Yeah. Okay. It's very concise, very brief, right? By contrast, what's the cause of an electric field?
A charged body.
A charged body, yeah, right. Mr. Luca, you want to do the next one? What is explain?
Yeah, but I also have a question.
Okay.
For the vector potential.
Yes, sir.
In the book, when it says like a specification of magnetic field, it also says in parentheses local.
Yeah.
What exactly does the local mean?
It means that the relationship between the vector potential and the B field, the A field and the B field, is simply they're related locally. So it's a further specification of the condition of the B field in that vicinity. So the change of the A field is related to the B field. In other words, the curl of the A field is the B field.
That's just saying that they're really closely related then.
They're related only on a local fashion, and not the A field over here is not directly related to the B field over here, right?
Okay.
It's only the curling of the A field in this vicinity that is the B field in this vicinity. So the derivative is a local change and not a non-local change.
Okay.
Okay. All right. So, but you're on the hook for number 2. Explain when the magnetic. I'm sorry about that. When the magnetostatic condition pertains and strict magnetostatic condition.
So wires don't move, and current is constant and in a loop.
Yes, current flows in a loop, and the current is constant, and the wires don't move. Right. None of the, and you could think it more generally. It doesn't have to be in wires, but we say it's in wires makes it pretty clear. But you could have a current distribution that's maybe not confined to wires, but is flowing through space, like in the heliosphere or something like that. We have the solar wind is flowing by the magnetic field of the Earth, for example. The condition for magnetostatics is that the current distribution doesn't change, and that the divergence of the current distribution is 0 everywhere. Right? Only circulates. Okay. What is the dimensionality of J if it is the charge current density? It should be volume, specifically the charge current volume density. Yes, Mr. Friedel.
So would that be charge per volume per time?
Charge per volume per time. Okay, so anybody want to quibble with that?
Is it just charge per time?
Is it just charge per time? So we have, let's see, we have two here. Charge per volume per time. Charge per time.
Or is it charge per area?
Or is it charge per area per time? We've got multiple choice A, B, or C, or none of the above. Yeah, Mr. Dowdle, what do you think?
C.
Mr. Dowdle is choosing this one.
Good. 'Cause I think
Mr.
like,
Bacot, what do you think?
Oh, it's area. It's area.
Ah, there it goes. It's installing an update anyway.
Without work.
Okay, Mr. Dowdle, what was your reasoning for going with C?
I think like the confusion between A and C is that we made earlier reference of a volume per volume.
Yeah.
So like the charge represents a volume. So and then it's going through and it has a flux through an area, and then since it's a current through a time.
Yeah. So a relationship that will help you is to remember that the volume current density is related to the charge density and the flow velocity. If you have some charge per unit volume that's flowing with a velocity v, then it produces a current density, and then it would be measured as a current density. And that can help. Then what is the dimensionality of rho? That's a charge per volume, right? Okay, and so if you multiply that by a velocity, then you can see that the current volume density is charge per unit area per time, which means that if you now collect this over an area, you get a volume per charge per time. So what should be here? Not J, but I. Good. That should be I. The dimensionality of I is charge per time, and the relationship between I and J is I is a product of J with area, or more specifically, vector relation there, where we have a current direction and an oriented area, right? Remember, the area can have an orientation, especially if we have a surface that bounds a volume, then we can give the area an orientation pointing outward from the volume. Everybody clear on that? Okay. Let's do a system update. I gotta somehow figure out how to turn that off. I don't use it often enough. Okay, what is Ampere's law, also known as Maxwell's fourth equation in the magnetostatic limit? And now I want both the differential and integral forms. Maybe that's best if somebody comes up here to write these down rather than trying to say them. So who would like to come write Maxwell's fourth equation, Ampere's law? Mr. Carson. Yes, sir.
Okay.
Please.
Which one?
Yeah, use that one. You running out of space over there?
Yeah.
Yeah. Okay, good. Good. What do you think? Anybody? Does it look right? Okay, looks right to me. This last piece here that's kind of running over the edge there. That, remember the relationship between the current density and the current. This is I. That's the I enclosed inside of that path. We have the B field. So this is the circulation of the B field around the path. C, some kind of curved path like this. And it's easiest if you conceive of it as a planar thing. And then you're looking at how much current flows through this. And that total current flowing through that path, of course, will be the I enclosed. And so the circulation of the magnetic field around this path is determined by how much current is enclosed by that path. And so in the first form, in the differential form, there's a causal relation, again, also expressed. The current density is a measure of the cause, and the B field is a measure of the effect. And in fact, what we're saying is that the current causes a curling B. And remember J here, because we're in the magnetostatic condition, divergence of J is 0, so J here really is also a curling J. It's only circulating. So a circulating J causes a circulating B. Circulating J is the cause of a circulating B. Right? Of course, they circulate in different ways, but there's circulation there. Mr. Bicot.
The first integral?
Yes, sir.
The ds, that,
Yeah.
that
Oh.
means the outside.
Ah, good. Thank you. Thank you. That I'm going to quibble with that. That should be a dl. So it should be a little increment here of the path, dl. So the dl is a vector that points tangent to the path. That's the direction of the vector in the counterclockwise direction. And the length of the dl is the little bit of the circumference of the path. Okay. So I think you wrote a ds there like a surface element, but it's not. This is a one-dimensional integral, although it doesn't have to be on a straight line, but it's one-dimensional in the sense that it just follows a path. And so it's a dl. And so B dot dl there gives you the circulation of B around that path. Was that what you were spotting, Mr. Picot?
I was just, yeah, I guess.
Okay. You know, when the dog runs at you, you whistle for him, right?
I don't know, I guess the letter S was like.
Yeah. Okay, so that
It's
should have
the
been a...
integral around the outside of the circle.
Yes, it's an integral around the outside, and so it's a one-dimensional integral, but it doesn't have to be on a straight line. In fact, it has to be a closed path. It can't be a straight line, only a straight line. Good. And the way this also, we say that this path, or this curved path, is the boundary to the area. So this area is this area here. This is the region that C bounds. And it's a closed path because it completely encloses the area. And that closure there is indicated by the circle here. And, okay, in fact, I'm going to quibble again here. Okay, Mr. Carson wrote a circle around that integral, but that should not have been like that. It should be, let's see, can I push up? No. Some things work and some things don't. It should be this. I'm going to rewrite it here a little more carefully. 4 pi over C over surface, but it's not a complete close. It's not a complete surface. That is, it does not enclose a volume. It's just a disk, for example, and the path around that, the circumference of the disk, is C. Okay, good. Yeah. So there were a couple of mistakes there that I didn't pick up on right away. Okay, good. So let's see here. Yeah, this thing went and updated itself when I didn't want it to. places too. Okay, so let's see here. Explain all of the symbols. So then you need to be able to explain those pieces, the integrals, the ones with the circle around them, the ones with the double integral, things like that. The DL, the DS, or the DA, all of those symbols you need to be able to explain. I didn't make Mr. Carson do that. He got away cheap. What is Maxwell's second equation? Also, you can just say it, right? That one's a quick one.
Divergence of B equals 0.
The divergence of B is 0. Always the case. B never diverges. Okay, that one will remain the same for us. It won't change. We're going to be modifying some of these others when we start relaxing the static conditions. We're going to start introducing other terms in Maxwell's equations, but that one will remain always the same. The magnetic field never. Okay, so given a magnetic field of measure B at some location, what's the force that would exist on a body of charge Q placed there and given a velocity V? Maybe that's worth writing down here because it's who would like to come up and write that? Mr. Picot. Yeah, on the big one there. You're going to need to use this. That's the force. Okay. And what system of units is that, Mr. Picot?
The CGS.
That's CGS. Good. Thank you. Anybody know what an SI? By any chance? Mr. McKenna? Remove the C. Right, yeah. An SI is pretty simple. Okay, so now in the case of the electrostatics, we had this. In CGS, can you tell me how does the dimensionality of B compare to the dimensionality of E? Looking at this equation, these two equations. B. So you're saying that the dimensionalities differ by a factor of charge? At least. Mr. McKenna.
Since they're both force, shouldn't the dimensionality be the same?
Yeah, they're the same in CGS. So this ratio here, V over C, is dimensionless, right? They're both speeds. So that's dimensionless. And then we have a Q out front. So Q times B is the same as Q times E in dimensionality. So they're the same. So in CGS, they have the same dimensionality in CGS. In SI, there's a factor of C different, a velocity difference in their dimensionality, right? Because there's a factor of C. I would remove this factor of C here in SI, so they're differing by a length per time dimensionality. So that's one of the simplicities of CGS. The B field and the E field have the same dimensionality in CGS, which is part of the appeal. Mr. Picot.
So if you cross two vectors, are you just multiplying the
Yeah. So let's take the question. If I have two vectors A and B, no, I don't want to use A and B because those have meanings here that we don't want to attribute here. So little a and little b. Okay, what is the dimensionality of the dot product of these two vectors? Well, it's the dimensionality of these two vectors. It's a product, right? And you can prove that by remembering the Cartesian form. That's one way to do it, or to remember the fundamental definition. Remember, the fundamental definition is the product of the magnitudes times the cosine of the angle, and the cosine of the angle is dimensionless. Or you can also look at the Cartesian form and see the same thing. Each component has to have the same dimensionality. Okay, the dimensionality of the cross product must also be the same. Remember, the magnitude of the cross product is the magnitudes times the sine of the angle, and the sine is dimensionless. Okay. Good question. Okay, let's see. So, what is the Imperial Metric relationship between B and A? Okay, so the relationship that we talked about before is that A is a further specification of B, but now there's an Imperial Metric expression of that relationship. That one's pretty simple. Maybe somebody could just say it.
B is the curl of A.
B is the curl of A. Okay. Good. Okay, what is this is going to require writing. What is the formal definition of the curl? So, and express the curl in Cartesian form. So we can do this in parallel here. We've got two. This one has stopped updating, so we can do this in parallel. Two people come up. One write the fundamental definition of the curl, and the other one write the Cartesian form of the curl. Mr. Fox, Mr. Williams.
Is the formal definition of what the integral is?
Yes, that's correct. Yeah.
Which one are you doing?
I'll do the formal.
Okay.
You want the?
He gave you the long one.
Sorry.
What's that?
I was seeing.
You're looking on his test.
I am absolutely copyright awful. You didn't even try this one. So.
I'll erase it for you. Okay, so Mr. Fox has written that the curl of a field W is the circulation of that field around a small. Well, actually, I should let him explain what he's written down. What do the symbols mean, Mr. Fox?
Well, let's see. We'll start with the single integral around a closed area, and W is a field that we're given, and then we're taking the limit, adding up little pieces all the way around that area, seeing what the circulation is, and then so you have the integral divided by the area, so that's over each little piece, and then we take the limit.
So this has a name.
Yeah.
What is the name of that? That integral, that piece. I said it just a few minutes ago when we were looking at the B field. Maxwell's fourth equation. This is called the circulation. Okay, that's the circulation of W around that path, around that area. Okay, and then you take the limit. That's the fundamental definition. It's strictly Imperial Metric. So there is a relationship between the curl and circulation. Where there's a circulation, there must be a curl someplace inside. But the curl may be zero, mostly throughout the region. It just has to be non-zero someplace. Right. Okay. And he notes down here, gives how a field changes perpendicular to itself. Yeah. Good. As contrasted with a divergence, which we covered in the previous chapter. Okay. Here's Mr. Williams' Cartesian form for the curl. And let's see here. Huh. Okay. Oh, yeah, that's right. I remember I have to do it up here when I'm using this form. That's right. Okay, here's an eraser. He was wanting to erase that piece there. Okay, so no, I will draw. Okay. All right. So, Mr. Williams, how do you remember the order of these terms?
The directions goes out in front, X, Y, Z,
Mhm.
and then the derivatives on the bottom goes in the same order, so Y, Z, and
Right.
then the components of J are just switched in each
Good.
little parentheses.
Yeah, the derivative goes first before the component, right? So first there's the unit vector x then the derivative is the y direction, and then the component of j is in the z direction, and then when we get this, we get yzx here, and then we get zxy here, and then we get the reverse. We take the contrary, the negative sign in front of it, where we swap the component of j and the derivative. Right? That's correct. I think all of those are correct. Yes, looks right. Okay, good. Let's see here. Let's switch back over to here. Okay, find the magnetic field associated with this vector. A is a constant, x and y are the coordinates. That's a natural log there. And the A field is in the z direction. The next one is pretty long, so I guess we'll just ask somebody to come up here, see if you can demonstrate taking the curl of this piece for us. So I'll write down A. A is in the z direction, A natural log of x squared plus y squared. Okay, take the curl of A. Right. I guess you have to remember that B is the curl of A, right? Because it doesn't actually say that. Is that right? The question is written, find the magnetic field. Okay, so it doesn't actually explicitly say this, so you have to remember that. I helped you a bit there, got you started. Oh, he's going to write down the determinant form. Okay, so this is a good demonstration. If you don't know the determinant form yet, it's handy. I find it easier to calculate things. So if you haven't learned it yet, it might be a good thing to learn how to use it, how to take the determinant.
And then this isn't all going to fit very well, but
There you go. Yeah.
so it's y.
Is that a y? Yeah. Okay.
It's also a y.
Anybody, Mr. Miller?
Yeah, there's an extra negative. If you have it subtracting that component, then it's a plus y, or one or the other.
So your y hat term has two negatives there. Why are there two negatives? The first one was because of the determinant.
Give me a second. Yes, that's not supposed to have two negatives.
Yeah.
So that would be plus.
Good.
So this eraser.
Yeah, there's an eraser on the side there. Right there, there's an eraser. There you go. Now it's right. Yes, sir, Mr. Miller.
Does it also work?
Thank you.
Yeah, this question. If you alternate or kind of do the determinant differently so that it's all positive x hat components plus y hat components plus z hat components. Because I do that and it seems to work. But I don't have to do the alternating thing.
I'm not sure. I don't quite understand your question. Hold on just a second. Let me.
If you use that.
Yeah, that's what I do.
This takes into account the negative.
Yeah.
So if you just
Because
do
you.
that, it works.
Yeah, because I don't
Okay.
know why you go backwards. I just do the same
Let me
thing.
first make a comment on this sign. If you see this thing here, what he had originally was yx hat plus xy hat. Oh, I see. But that doesn't actually have a circulation to it. So there's no, and you should expect a circulation because you're taking the curl of something. So you should expect something that circulates because you're taking the curl, and curl circulates. So curl does not diverge. Remember, you worked out an exercise where you showed the divergence of a curl is 0. So that means the curl itself also has a curl and not a divergence. So that has no circulation, whereas this you probably hopefully should remember from sketching these enough that that's got a circulation to it. Okay, and that might have been a hint to you. Okay, now Mr. Miller has a question about signs. Is it something we can do here?
If you go back to where you had the curl expanded.
Yeah, what? Uh-huh.
Oh, wait, that was on the other one.
Uh-huh, on the previous.
That was on the tablet.
Oh, yes, he had it on the tablet. Yes, Mr. Williams did it. Okay. Yeah?
If you use the determinant
Uh-huh.
kind of just a little differently, you
Uh-huh.
can get that.
Okay.
Where they're all positive.
Then it's all right. Whatever, if you get
Okay.
that right, then it's right.
Okay. That's a good, okay.
The unconventional Miller method.
I like all positives.
You like all positives, but half of them have to come out negative, right?
Yes.
Okay.
Yeah, it's just it's kind of the negatives pushed inside, so everything's flipped around.
Oh, okay.
So the Y's flip.
Okay.
It's like that.
All right. Okay. That's a little unconventional because the determinant involves the alternating signs.
Yeah.
Right. So you're taking the determinant
Yeah, I
a
just
little
do
bit.
the determinant one step differently. So
Okay.
that
All right.
flips it.
Okay. Then that should work. Did you have a question, Mr. Downey?
Oh,
You
I
have a
was going to
question?
volunteer for sure.
You're going to volunteer. He's jumping ahead. All right. Good. Let's see. Where are we? Okay, so the next one is a little bit more involved here. Use Ampere's path law to determine the magnetic field inside and outside of a long current carrying cylinder, far from the ends. Okay, be sure to specify all the steps in the derivation. I'm happy if you want to just say those in words rather than writing them all down. And then make a sketch of the magnetic field. Okay, Mr. Dowdle, come on up. Choose that one.
Oh, never used this before. So.
Yeah, the question is whether it's a hollow cylinder or a solid cylinder. So, Mr. Dowdle, what do you imagine there? Is it a hollow cylinder or a solid cylinder?
Solid.
You're taking it to be a solid? Okay.
Yeah.
And the current density is distributed uniformly over the cross section of the cylinder. Is that what you're imagining? Okay. All right.
Okay.
It's ambiguous, so that is a question. So you have to really, to give a good answer, you have to say which one you're going to assume.
Does it make a difference?
Yes.
For the outside?
Certainly. Oh, not for the outside, no.
Okay.
Not for the outside. Makes no difference. But it does
Yeah,
matter
for the
inside.
inside.
Yeah, it does matter inside.
How do you erase? Oh, actually,
There's
that's
an
pretty
eraser right here if you need to. You can touch the eraser.
That's pretty much multiplication. So
Okay.
Trying to say where. Say this to be.
So R naught is the radius of the cylinder. So outside that magnetic field looks like that. Ah. So let's see. He's actually made an assumption here. Let's see. Why can you go from this step where you have the vector, the dot product of the two vectors, to here a form where there are no dot products, no vectors left anymore?
I think because the two vectors kind of cancel themselves out. It's like x hat equals just 1. So. Can you do that? Kind of like the same way like we did before, like I think it was dA, like EDA.
Yeah.
I mean, vector E dot D, vector dA is equals EDA.
Yeah, because the two vectors are parallel.
Yeah.
Right, that's
Okay.
what it is.
Yeah.
B is parallel to DL. B is running tangentially. It circulates around
Okay,
that path. So it circulates around the wire, so they're parallel to each other. Okay. Let's see. There's one thing though I want to point out, and that is you say that the B field is 0 inside. So what does that make? What assumption does that make about the current distribution inside the wire? If you follow this same argument again, let's suppose you take that same path but shrink the circle.
Okay.
So the radius is less than the radius of the cylinder.
Yeah.
Does that say that I is 0?
Oh, that's okay. Yeah.
So where is the current distribution then?
The current distribution has to be outside of the
Yeah, it's on the
radius.
skin of the cylinder.
Yeah. So that's on the skin of it.
Okay, so that's the assumption that you made. Now, so thank you. How would we? Let's look at what would happen. Let's go through Mr. Bacot's question. Does it matter? Let's suppose that the current distribution is uniformly distributed over the wire rather than being simply on the skin. So now I'm looking at a cross section of the wire. I could have a situation where the current is just only on the skin of the cylinder. That's a possibility. I could have a current that's distributed uniformly over the area, cross-sectional area of the wire. Of course, there are a lot of other possibilities, right? These are two simple ones. There are other situations that are possible. Okay, now in this one, if the Amperian loop is inside, then there's no current inside. So the enclosed current in this case would be 0, and that's why the magnetic field would be 0 inside of a wire current distribution like that. But in this case, if the current distribution is uniform, you actually have some current inside as long as you have a finite radius. So how would we calculate the enclosed current then?
I over R naught times R.
R
Ratio.
over ratio of the radii?
Yeah.
J dot dA.
Weight squared ratio, or radii squared.
Radii squared,
Because
right?
area.
J dot dA. Mr. Friedel is remembering that the current is J dot dA, so it's the current times the area. So it scales like the area. So it would be the ratio of the areas, pi r squared over pi r squared naught. R naught squared. Do you see that? The enclosed is going to be the ratio of the area of the loop divided by the area of the cylinder. And in proportion to that, the current is going to be some fraction of the total current. Okay, so now if we did that, let's go see how it would modify this. We have 2 pi RL, 2 pi RB, excuse me, 2 pi RB. That's the circulation of B. And this is going to be 4 pi over C times the enclosed current, which is the total current, times the ratio R squared over R naught squared. And this is for R less than R naught, for a uniform current distribution. Okay, so now we have B is going to be 2I over C R naught squared R. So the total solution then for the uniform distribution is inside and outside. We could write it like this. Inside is 2I R over C R naught squared, and outside is 2I over C R. That would be for the case of the uniform current distribution, whereas in the case of the current flows only along the wire, on the outside of the wire, so this is uniform, and along the outside, on the skin of the cylinder. then in this case it would be B is 0 inside. See the difference there? Okay. This is more, the top one is more continuous. Mr. Picot.
When R naught is less than R,
Yes.
the 2I over CR, the R is the radius of the big circle, or
Yeah, the Amperian loop, the imaginary Amperian loop, right? So, yeah. And where R naught is the radius of the physical cylinder, the wire itself. So in the two cases would be B is 0 and then jumps up to something that falls off like 1 over R, or the other case, which is the uniform case, is B is linear like this, ramps up linearly and then falls off like that. Okay, so that was generally good, except for that question that was kind of left open there. It was ambiguous. The question is ambiguous there. So if you face an ambiguity like that, you can choose, unless I tell you a general distribution, which would be kind of complicated in this case. So you're free then to choose something more specific. And in fact, if you actually are aware that you have chosen that, then and say so, right? Say this is an ambiguous question. I've chosen this. I actually like that. It might give you an extra point for noticing that ambiguity in the question. Oh, previous problem. Now we construct a magnetic field around a coaxial cable. Okay, now the coaxial cable, the current is on the cylinder, the surface of the cylinders. There's no uniform distribution, so that kind of implies that I had in mind for number 6, I had in mind that the current was on the skin there, because you really can't use it for the next problem. That's why I'm not using this test anymore. Okay, so what would that be then if we have a coaxial where the inner coax and the outer coax have current flowing in the opposite direction. The inner one is just a very thin wire, and the outer one has a radius R naught, or let's call it R naught to keep it consistent with what we were just doing. What does the magnetic field look like here? You can just superimpose solutions from the previous problem. That's one way to do it. That's quicker because you've already gone through the Amperian argument. So what would it be then? How would the magnetic field inside of R naught, outside of R naught?
In between the two, it's just 2I over CR. And then it's
2I over C
CR.
R. Good.
And then outside it's 0.
It's 0 because they cancel. They have magnetic fields generated by the two current distributions will cancel in the outer region. In the inner region, it's only the innermost wire that generates the magnetic field. Yes, ma'am?
So how do they cancel if they're propagating outward and it's at a farther distance from like the field from the one in the center has propagated farther to get to the same point on the outside, and so it would be slightly smaller?
Only some points, right? If we take a look at the cross section of the coaxial cylinder cable here. I think she's asking here, why is the magnetic field 0 here if it's traveling farther to get from the center wire than it is from the outer cylinder? But actually, parts of the outer cylinder are traveling farther also, right? This part is farther, is the farthest. And so they are the same, but it's only if you take into account that there's actually many different distances contributing in this case, and you have to add up the influence. And that would be the same then as though it had been concentrated at the wire. Does that make sense? Okay, same thing happens in electrostatics. If we have two charged spheres, spherical shells with opposite charge distributed on them, and we're out here looking at the electric field, there's no electric field outside of that because the electric field falls off, and we get some electric field from over here, and this is closer, but this is farther, and so it's the same as though it were concentrated at the center. Yeah. Mr. Picot, you raised your hand?
Oh, did I?
Oh.
I don't think I
It's like Dr. Strangelove, your hands go. What? Yes, sir, Mr. Hetherington.
Do you want us to say what direction it's traveling?
Yes, right. So the magnetic field direction, specifies the strength but not the magnitude. And so back here in this case, going back to this one, what is the direction of the magnetic field?
Perpendicular to R.
Yeah, it's perpendicular to R. And if I is coming out of the page, well, he's drawn the direction of J here. Okay, so there's the current. He's given us the direction of the current here. And so we're looking on here where the current's coming out of the page, and I don't want to. So the current is on the skin here. Which way is the magnetic field?
Counterclockwise.
Yeah, counterclockwise. The magnetic field will look like this. Good. Yes, and I would like a sketch of the I asked for a sketch of the magnetic field, so you should demonstrate that sketch. It falls off like 1 over distance. Okay, good. And God bless. Class is over here a little bit, but here is, so we'll just say this very briefly. Working from memory, describe a current distribution that would generate a uniform magnetic field. There are really 2 simple ones that would do that. What would they be?
2 parallel plates in opposite currents.
2 parallel plates carrying current in opposite direction will generate a uniform magnetic field, just like a parallel plate capacitor generates a uniform electric field. What's another?
Solenoid.
A solenoid. Inside the solenoid, uniform. Okay. And then, of course, in this case, you have to say uniform in some region. You have to be far from the ends of the solenoid or far from the edges of the plate. And the plate separation should be less than the big distance and so forth. You have those conditions. And the, okay. And the solenoid has to be